I would invite now the next speaker from the same group. As Professor mentioned, there are 3 papers from Japanese group. So it will be presented by Mr. Yoshida, and the title is Dynamic Fragmentation of Ice Spheres, 2 spheric fracture patterns. Please.
Thank you for Jefferson. I'm very glad to speak to you today. I'm Tomoyoshida from Tokyo, Japan. This work has been done with different colleagues. Today I'd like to talk about 2 specific fracture patterns due to impact on ice fields. Here is today's content. Then introduction. Ice particles can be only found not only once, but also in space, as in the rings of Saturn, like this. And also, their closeness to our living environment, the mechanical properties of inelastic collision and the dynamic fracture and fragmentation of ice materials have not been completely clarified so far. And in a ring system, energy loss during collision of particles may play a crucial role in determining not only the mean free path between collisions, but also the physical characteristics of the ring, such as kinematic viscosity, spring rate, and the rate of cooling in the system. And the coefficient of restitution is a key parameter for evaluating such energy loss during collisions. And note that ice particles in the major rings of Saturn, the size of ice particles varies from several centimeters to several meters. And their typical relative speed before collision is some 0.1 centimeter per second. Therefore, in order to better understand the mechanical characteristics of ice as a solid or granular material and acquire more quantitative information about the scaling effect of impact velocity on the collisions of ice materials, we have experimentally observed the mechanical behavior of an ice sphere impinging upon a plate of ice with a high-speed digital video camera at a frame rate of 7,000 frames per second. And from this slide, I show you these experiment photographs. And in this time, we use ice spheres whose diameter is 25 millimeters. And then ice spheres are falling, and after the in this photograph taken, ice sphere is just on plate, and then they are rising with no fracture. And that graph is relation between the relative impact velocity and the restitution coefficient, which is gained from the experimental one and the theoretical ones. And by using these data and numerical methods, which is event-driven methods, we have conducted the numerical simulations of the cooling system, which is 3,000 ice spheres collisions into account. And here, this graph shows the results, and this graph shows that if not only considered with not only variations of the system temperature and with its fluctuations of restitution coefficient into account, the final temperature is 4% lower without fluctuations into account. And our second series of laboratory experiments involves the fracture and fragmentation of the impinging ice spheres. The diameter of an ice sphere is this time 50 millimeters, and 7 different falling distances between 2.15 and 2.7 meters have been set. And this time we have recorded collisions of 200 ice spheres against a flat polycarbonate plate by the same high-speed digital camera, but at a frame rate of 150,000 frames per second. And this time, we can find only two representative fracture patterns, and that is this one and this one. Experimentally taken photographs illustrate representative dynamic fracture development in ice spheres upon collision against a transparent polycarbonate plate. And there are all side view. Also, both ice spheres have been prepared under the same conditions. The sphere shown on the top, this is split into several segments of large and similar size, and we called it orange segment type fracture pattern so far. While that at the bottom, this is fractured only near the lower surface and the large part of the sphere is not broken, and we called it top type fracture pattern so far. And from this slide, I show you a series of photographs in this experiment. And note that the left one is orange segment type fracture pattern, and the right one is a top type fracture pattern. And in the right photographs, some cracks are developing along near the surface from bottom impact point. And then finally, this fracture is like this. Sorry. And after then, we conducted further experiments involving ice fracture. This time, the diameter of ice sphere is about 60 millimeters, and this time we have used new receptacles that produce more single crystal-like transparent ice spheres, and we observe the dynamic fracture induced by free fall and collision of ice spheres with the high-speed digital video cameras at frame rate of 10,000 frames per second. And this time, we also recorded from top view. And this time, also both fracture patterns have been recognized repeatedly during the experiments. And these further experiments to show the presence of the two specific fracture patterns even without the pre-existence of apparent material inhomogeneity such as air bubbles in spheres. And here are the photographs of these experiments. And the top four photographs are the fracture of top type fracture pattern, and the bottom four photographs are the orange segment type fracture pattern. And this experiment data shows that both fracture patterns have been recognized repeatedly, and even without the present existence of apparent material inhomogeneities, this both fracture pattern has been recognized. And then we have investigated the histories of stress and deformations in model linear elastic ice spheres and tracing wave and fracture propagation using our finite difference scheme. Here, typical contours of normalized octahedral shear stress, and note that this time we use no fracture involved scheme, and we supposed linear elastic and homogeneity and this. And this time we show you two patterns of snapshot. And the left one, the normalized duration time of impact is 0.8, and in the right one, the normalized time of duration is 8. And in the left snapshot, the surface waves are induced and propagating from bottom to top along near the surface, and then rising and finally like that. And we can say that the left snapshot indicates top type fracture patterns. On the other hand, in the right snapshot, we can find quasi-static propagation throughout four photographs. So we can expect in this case, orange segment type fracture pattern is expected. By these preliminary numerical speculations that are explained before, the duration of collision or the length of the sphere plate contact time seems to play a crucial role in comprehending the generation of two fracture patterns. However, in the calculations, the impact load is given at the bottom as a simple function of normal compressive stress only, which in reality may not be mechanically true. Therefore, more rigorous simulations based on the discontinuous Galerkin methods that include also the mechanics of dynamic contact between the sphere and plate are performed in order to verify whether the above finite difference speculations are at least qualitatively acceptable or not. And in this time, this DG methods-based simulation, the sphere is supposed to be axisymmetric, and the mesh is much finer near the contact point. In the left above figure B, the maximum of the shear stress criterion is plotted. And the result shows that an important concentration of the shear stress acting on the plate or Z in the compression zone is remarked near the point of impact. Therefore, the fracture may occur in compression, giving the top type fracture pattern like this. And in the left above figure D, the maximum of the principal stress is plotted, which are mostly in oscillator direction. And it shows that near the impact point, a compression zone prevails, but on top of it, a tension area is present. Therefore, the fracture may occur in tension, resulting in the orange segments type fracture pattern, like this. Conclusions. We have again recognized two specific fracture patterns. The one is top and the other is orange segments type fracture pattern in the new dynamic laboratory impact experiments of free-falling ice spheres without initial material inhomogeneities. And now we are currently measuring the more exact and quantitative information about contact during each impact with laser displacement sensors and pressure sensors. That's all. Thank you for your kind attention.
Thank you very much, Mr. Yoshida. I think we have time for maybe one or two questions, 1 minute. So if you may have any question, please. Yes,
can I ask you, these two works, they were made by one high-speed camera or different ones? And I would like to know what is your frames per second rate? What is the possibility?
Should I go back to yours?
because it was stated 1,000 and 50,000. Yeah, it was different. Two different data were given in previous and
Here, if you read your previous presentation.
50,000 and now maybe I see 100,000.
In this
7,000.
No, that is the old one. No, later, not later.
150 and 10,000 frames per second. And only this time we use another fast cam photo Ecam Max.
So we have two high-speed cameras. One is very old, so with the old one we have 10,000 and white and black photographs. And we have now a new one, so full color. And with that new camera we have 150,000. Yes, that's all I remember. Yes, so we have two cameras.
Okay. Thank you.
Yes, please.
And what is the method of dynamic loading? The same as in your presentation?
No.
With mine we use electronicity.
Yeah.
Yes, and rapid evaporation.
Yes.
This one is very simple, just free falling. Yeah, from 2 meters or so. And we have found only 2 fractures, no other.
Thank you very much.